In this short video, we'll look at energy from an atomic point of view. So Newton and others pre-1900 thought that energy was continuous. And that's because people like Newton, they were looking at stars from a long way away. And from a distance, energy seems continuous because you lose resolution whenever you view something from far away. But actually, energy is discrete. So the opposite of continuous is discrete. Now this idea of energy being discrete means it comes in pieces or quantities. So some quantities are not allowed, some quantities are allowed. And quantities, the plural of quantities is quanta or quantum. So one quantum or two or more quanta. One quantum or two or more quanta. And this is where the name quantum mechanics came from. So quantum mechanics, or the mechanism of how discrete energies or systems with discrete energies operates, is what we're looking at currently. So energy is h nu. This was Max Planck's equation. Which he developed around 1900. We don't need to go into too much detail about this equation in this class. There are subsequent classes for that. But we need to point out something important. Here, h is a constant, known as Planck's constant. E is energy. This symbol here, it's a Greek symbol. It's the letter nu. Nu is frequency. And it has the letter nu. So E equals h nu. Importantly, energy is proportional to frequency. If we take the equal sign and the constant to be a proportional sign, then energy is just proportional to frequency. So I'm going to erase the board real quick and keep it in the same video, and then we'll spend a little bit more time looking at this idea of energy and frequency. So we know that energy is h nu, or importantly, energy is proportional to frequency. So if anybody watching this plays a musical instrument, this will be a way to think about it. If you take any musical instrument that has strings, for example, let's say we have guitar strings or violin strings. Then you know if you were to pluck one of these strings, it would vibrate and it would give a certain energy. The energy would be the pitch of the note. If you were to, for example, put your finger in the middle of the string, so if you were to put your finger here, there's a finger, in the middle of that string, you would effectively make that bottom string shorter. That bottom string would have be a higher note than the original lower note. Okay, again, we're just considering plucking a string in a musical instrument. If you were to put your finger in the middle here, you would effectively make it shorter. Well, putting your finger on a string is something that a musician would do. The language we would use to describe this in chemistry would be a node. So here we increase the number of nodes. So originally I had node, node. So if we look at the original length of the string, I had 2 nodes. That's where the string can't move, or a place where the energy is 0. So the energy equals 0 at the node. But by putting my finger in the middle, I add an extra node. So I effectively add an extra node in the middle. So I've increased the number of nodes. By increasing the number of nodes, I effectively make the note higher. So I can see that the energy is proportional to the number of nodes. The energy seems to be proportional to the number of nodes. What would the number of nodes do? The number of nodes would increase the frequency. Now, if the energy is proportional to the number of nodes, which you know because the note gets higher, and you already know that energy is proportional frequency, we can deduce that we can deduce that the frequency is also proportional to the number of nodes. Another way to think of this is if you were to actually draw a wave onto this. So if you imagine a wave oscillates about the center point. You imagine a wave oscillates about the center point, then if I were to put a node here so the energy is 0, I could put another node here so that the energy is 0. I could put another node here so that the energy is 0. So I can have nodes wherever the energy is 0. If I now put a node in the middle, so let's put a dashed line, well, that's okay, I can have 0 energy, but that's convenient if I have exactly a wavelength, so a reproducible wave, and I have my node right in the middle. But what if I had put another node in here? Because I don't know exactly where my node goes. I'm just randomly, if I put my finger on a guitar string, I have no idea if I'm chopping a node in half or not. What if I were to put my node right in the middle? Well, then I wouldn't be able to, that wouldn't exist. It wouldn't be, I'd basically chop this information in half. So if this happens, what would instead happen is I would have to change the pitch of the note. The note would have to respond by having a 0, by having a node in the middle. So I could do this, or I could do this. Whatever I do, I've got to adjust so that I have a node, or where the node is being placed, I have 0 energy. So by introducing a node, the note adjusts so that it has 0 energy at the node. And in all cases here, I now have more lines per unit space, per unit distance. So I've effectively increased the frequency. So again, I can make another video, but this, at least if you watch this video, it shows you this idea that nodes are proportional to frequency. I add more nodes, the node adjusts to add a higher frequency, both of which are proportional to energy. And this was something that was realized for matter around 1900.